function has as many zeros, meaning numbers that you can plug in for x that will result in an output of 0, as it does the highest exponent in that function. So if we take a look at this first one, the highest exponent is 3, so that means there are going to be 3 zeros, 3 numbers that we could plug in as values for x to generate 0 as an output. We may have all real zeros, there may be some imaginary numbers that work as well, but altogether there's going to be a total number of 3 numbers that create 0 as an output. In the second example, we've got 4 as the highest exponent. Again, I'm ignoring the leading coefficient in this case, I'm just concentrating on the highest exponent, so I'm going to have 4 zeros. There are 4 numbers that when plugged in for x will result in 0 as an output. So a function always has as many zeros as whatever the highest exponent is. Now, depending on whether a number shows up an even number of times or an odd number of times as a 0, so basically once or twice, dictates what it's going to look like on our graph. So if we look at these 3 locations here, so I'll circle those in those spots, the graph is passing through the x-axis at each of those locations. So that means that for all of those, we've got 1 0 each, meaning that the 0 appears if we were to write this function in factored form, which we'll look at in the future. Each of those would appear 1 time as a factor for each of those zeros. What's different is this second spot right here. This first spot, I should say. This first spot along the x-axis where it bounces off of the x-axis rather than passing through means it's a double 0. It appears an even number of times. So as a factor, it would show up twice in our equation rather than just once. So that's the difference between what we refer to as a double 0 versus a single 0. And so we would count that location twice if we were trying to total up the number of zeros, like we're asked to right here. If we wanted to determine the total number of zeros that this function has, we'd count this 1, 2, and then 3, 4, 5. So we'd say that we have a grand total of 5 zeros for this function. Now the leading coefficient test can tell us whether the highest exponent is going to be even or odd. Now that is kind of given away by our answer on this last question here. So we can see that we've got 5 zeros, counting that first one as a double and then all the singles. So that leads us to conclude that the highest exponent should be 5. We can also say that we know just without even counting the zeros that the highest exponent needs to be odd because we have a disco graph. So remember, if we're going up on one side and then down on the other, we call that a disco graph, and that means that whatever the highest exponent of this function is, it must have been an odd number to generate that type of graph. If the highest exponent was even, then we'd be looking at a touchdown graph. Both sides would be going up or both sides would be going down. And then finally, to determine if the leading coefficient is positive or negative, we need to judge based on which side is up and which side is down. So we established that the highest exponent is odd because of the disco shape, but now because it's going down on the right-hand side and up on the left from our previous work, that tells us that we have a negative leading coefficient. And so if, let's say it was x to the 5th, if I plug in a positive number, if I plug in larger and larger positive numbers for x, I'm going to get positive numbers out of x to the 5th, but I need my graph to go down, so the only way I could do that is if my leading coefficient was negative to turn that output into a negative. And then the flip side, if I plug in a negative number for x, raise that to the 5th power, I'm going to get a negative, odd number of negatives, it's going to mean it's going to be negative, but then I multiply it by the negative coefficient, and so that means I'll end up with a positive, meaning I'll be going up on that left-hand side. So that's how I can determine, using the leading coefficient test, without even counting the zeros, whether it's an odd or even highest exponent, and whether the leading coefficient is positive or negative. Now, as I mentioned, sometimes we can have imaginary numbers that are zeros, that if we plug in 2i into the function, or negative 2i into the function, it will also generate 0 as an output. But if we're looking at an xy coordinate plane, there are no imaginary numbers that are present, so it's not like we're going to be able to look at the graph and see a specific location that indicates that we have one of these imaginary or complex zeros. Instead, the evidence that this type of zero is present is by a change of direction in the graph that doesn't cause it to cross through the x-axis. So for example, here I have a change of direction, but I cross through the x-axis in a couple spots. Here's another change in direction, but I'm crossing through the x-axis in a couple spots. But here we have a couple of changes of direction, but we don't dip all the way back down to the x-axis. The way I describe it is I say it doesn't have enough oomph to get us all the way back to the x-axis. So that's an indication that we are going to have some imaginary zeros. Now if we clean up our picture here, for the directions we're asked to determine how many real and how many imaginary zeros it has, and we're told that this is a 5th degree polynomial, meaning the highest exponent is 5. So that means it should have 5 zeros. It should have 5 numbers that when plugged into the function generate 0 as an output. Well, here I see 1, 2, 3 of them. That accounts for 3 real zeros, and then that means I must have 2 others based on this change of direction here that doesn't get me all the way through to the x-axis that must be imaginary. So we can say we have 3 real and 2 imaginary, or we could call them complex zeros. In the second example, now we're told we have a 4th degree polynomial, meaning the highest exponent is going to be x to the 4th. But we look at the graph and we only see 2 spots that the graph is crossing through the x-axis. So that accounts for 2 real zeros. But we have this change of directions here, a couple of them, where we don't make it all the way back up to the x-axis. So that's an indication beyond the fact that we were told it's a 4th degree polynomial and we observe only 2 zeros, that there are 2 imaginary or 2 complex zeros. We can use those terms interchangeably. So again, the idea is we can't pinpoint a specific location on the graph that tells us that there are imaginary zeros, but it's these change of directions here and here that normally would dip all the way to the x-axis or rise all the way up to the x-axis in the second example, but it doesn't make it all the way there, and so then as a result that's an indication that there are some complex zeros. So in our last examples, we want to take some given information and then sketch a graph based off of that. Now we're not worried about any specifics, whether where we're crossing through the x-axis or anything like that, but we just want to use the general information that's given to us to get a plausible sketch. So we have to unpack the information that's given to us. So to start off with, we're told we have a 3rd degree polynomial, meaning the highest exponent in this polynomial is x to the 3rd. So that tells us a few things. Number one, it's going to be a disco graph. One side is going to be up, one side is going to be down. Now which side is which is told to us by the second piece of information. We're told we have a positive leading coefficient. So meaning it's like 1 times x to the 3rd, or 2, or 5, but it's a positive number out front. And so what that tells us is that the right-hand side, as we go farther and farther to the right, that side of the graph is going to be taking off to positive infinity, while the other side, when we plug in negative numbers for x, if we go far enough to the left, that's the side that's eventually going to go down. So we know that's the case based off of the leading coefficient test and the 2 pieces of information that we're given. Now, because it's a 3rd degree polynomial, we know we have 3 total zeros, but we're told that only one of them is going to be real, while the other 2 are imaginary. The fact that there's only one real tells us that there's going to only be one place that this graph is going to cross through the x-axis. And then there will be another change in directions that won't have enough, like I said before, oomph to get us all the way back to the x-axis. So one option as to how we could draw this, I could cross through the x-axis here, and then dip down, and then take off and go back up without making contact with the x-axis. Or another option would have been, I could have had that change of direction down here, and then only had that one place where we cross through the x-axis right there. So either the red graph or the purple graph would satisfy all these requirements. 3rd degree, meaning it's disco, positive leading coefficient, means it's going up on the right and down on the left, and then 1 real zero, meaning it only crosses through the x-axis one time, but it must have a second change of direction somewhere to account for those two imaginary zeros. Doing the same thing for the last one, we have a fourth degree polynomial. That tells us the highest exponent is going to be something like x to the fourth or x to the sixth. That tells us that it's going to be a touchdown graph. Both sides are going to be going up or both sides are going to be going down, one or the other. How do we know which? That's the second piece of information. Negative leading coefficient. So that means it's like a -3 in front here. Well, from our experience with the leading coefficient test, that tells us that both sides are going to be going down instead of up. And then finally we're told we have a double real zero. And so from our previous examples there, we know that that means that the graph is going to bump off of the x-axis someplace. But then we also have two other real zeros on top of that. So for our grand total of 4, since it's a fourth degree polynomial, all of our zeros are real. It's just one of them is a double zero. So one way that I could sketch that is I could bounce off of the x-axis there, but then I have to go back up and through the x-axis a second time and a third time here and here to account for those two additional zeros. So here's my double zero right there where we bounce off of the x-axis, and then here are my two single zeros giving us a total of 4. So any sketch along these lines, again, we could have drawn it a little differently where maybe we go up and then we dip down and then we go back up and then we go back down again. So here's a 0, there's a 0, and there's our double. However we want to do it, we just need to make sure that we satisfy all those requirements. Touchdown graph, going down because of the negative leading coefficient and the even exponent, and then the bounce at one location and the pass through at two others.